All right, grade 12, something we did last class, but only a few people were there on Wednesday. I just wanted to quickly cover it, and you guys have the video here. So we're going to look at radioactive decay and half-life. Before that, you guys were introduced to the modes of radioactive decay: alpha decay, beta negative, beta positive, and gamma, so you can recognize the reactions. But now, in this little video, we want to figure out what are the rules behind why a radioactive substance decays. Okay, so here you have a device called a Geiger counter. It's what we use to measure radioactive decay. So if I take this meter up to a radioactive substance, it's going to start to click, and we get numbers on it. And somehow when we interpret those numbers, that would tell us about the number of radioactive decays, the number of alpha particles that are being emitted, or beta particles, which refers to the number of atoms that are actually undergoing a radioactive decay. This is Chernobyl. I told you guys to watch that series. It's excellent, and you can see it's still very radioactive, and we can't go to that zone. And a reason for that, and it'll be radioactive for a very long time, is because the isotopes, or the atoms in there, have a very long half-life. So we're going to try to learn what the term half-life means. Okay, so if something has a very long half-life, the radioactivity will be persistent for a very long time. Here's a graph of a radioactive substance called cobalt-60, which undergoes beta decay. And if we took the Geiger counter up to the substance and started looking at the decay, I would notice that the meter would go down over time. Okay, so and the graph would look something like this. So if I waited there for a very long time, each one of these numbers over here represents a half-life. Okay, if I waited for 5.27 years, I would notice that the number on that meter would go down by half. If I waited another 5.27 years, I would notice that that number on that meter would go down by half again, half again, half again. So let's try to figure out how this meter works and how to work with these graphs and how to understand half-life. So first of all, how does a Geiger counter work? How do we detect ionizing radiation? Well, it's a pretty simple device. It's basically a very large battery connected to a simple circuit, except one of the leads, it's kind of like the vacuum tube I was showing you for Thomson's experiment, where you have an electrode here, an electrode here, and a bunch of gas in between. Okay, so we've seen that kind of a tube setup before. And if that gas is neutral, filled with like a neutral gas like argon, there would be no current because there would be no flow of charge. But when ionizing radiation comes in, such as a gamma ray or an alpha particle, it's going to go inside this material and it's going to rip electrons away from those gas atoms. When those atoms become ions, they become charged, and then they will allow current to flow. An electron will hop back into that atom and then neutralize it. Okay, so every time a piece of ionizing radiation, like an alpha particle, comes in, you're going to hear a click on that Geiger counter. It's going to register a number. Okay, so it's able to count every time an ion is formed in that gas chamber, okay, by an ionizing reaction. All right, so every click represents an ionizing event, and you can go backwards and say every click represents an atom undergoing a decay. All right, so an atom is undergoing a decay. So the more clicks per second, the more atoms are undergoing radioactive decay. So just again, the ionizing radiation causes ions to form in this gas chamber. The gas ions allow current to flow, and every click represents an ionization event. And the more clicks you hear, the more decays per second are occurring from whatever source you're looking at, which means that that source is more radioactive and more dangerous. Okay, and that's a very useful tool. Okay, we use it often in science if we're working with radioactive materials to try to figure out, to track. Radiation is very nice to track things in medicine, so we're able to then track where medicine is going using Geiger counters by tracking the flow of radiation. So it's not all bad stuff. Okay, another thing to understand though, if all of a sudden you're in a room and the Geiger counter goes off, so let's say I have a sample over here, and this is my Geiger counter. I'm going to call it the GC, okay, with a tube over here, okay, and it starts to go off, okay. If I want to minimize my dose, okay, remember this is radiation is like light, so what would you do if you want to minimize your dose? Well, you can put up a barrier, okay, which you've read in the section before, paper or lead. Different types of radiation requires different barriers. Or because it's light, and we just talked about power, remember, power and light intensity, let's talk about the intensity of the source of light is going to be equal to power divided by 4 pi r squared. So if I just double my distance away from that radioactive source, okay, it follows the inverse square law. Okay, the amount of radiation I'll be getting, the number of clicks per second, is going to go down by a quarter. Okay, so 1 over 2 squared is equal to a quarter. All right, so if I double my distance, the intensity of radiation is going to go down by a quarter. If I double that, it'll go down by 16. So if you're ever in a radioactive situation, just keep doubling your distance away from it, and you're going to decrease the intensity of radiation that's hitting you, because it is light. It is like light, it's radiation, and it follows the inverse square law. Just wanted you to think about that if you get a question like that on your exam. That's the easiest thing you can do to minimize your dosage of radiation. Just get away, okay? So what are the units of radiation? Well, the universal SI unit is called becquerel, okay, which would essentially counts the number of clicks per second on a Geiger counter. And remember, each click represents the decay of an atom. So we call it, like a becquerel is kind of like let's change the color here. Becquerel is a decay per second, okay? And that's your SI unit, okay? But if you go into medicine, they don't often measure becquerels. They actually measure the dosage that you have just absorbed, okay? So just because the thing is clicking doesn't mean you've absorbed all of that. But becquerels is what we use in physics, so you'll see that on problems in SOCO's text that you have to practice. They'll say the radioactivity of a substance is 1,000 becquerels, which means 1,000 decays per second. You might see curies, but we don't use that in our book. Okay, it's just another unit of becquerels because it can be quite a lot of becquerels. Okay, and then in medicine, we look at a variety of different units. Okay, so often the units we look at is sieverts or Röntgens. Okay, and that depends on the dosage that you've absorbed per kilogram. So everyone that works with radiation has a limit for the year of how much dosage that they could absorb. And it's measured in coulombs per kilogram. So coulombs comes from the actual ionization. How many coulombs of charge has just flown through the Geiger counter per kilogram of your body, okay? So you're always working with a Geiger counter. You have a badge on you that measures the coulombs of charge it absorbs, okay? And then it converts that into Röntgen. And then as soon as you reach a certain limit, then you're not allowed to work with radiation anymore, like I talked about. Okay, and Gray and Sievert are all conversions of this coulomb per kilogram. In IB physics, we don't really have to worry about this too much, but it's important for you guys to understand why there's different units for radiation if you try to look at it online. But we mainly look at becquerel, which is the decays, the clicks per second. So what do we use with that? So 1 becquerel is 1 decay, 1,000 becquerels is 1,000 decays. Well, now that we can detect radiation, we're able to study it, okay? So if I look at a radioactive source, I can detect different types of radiation, okay? And before we move on, how do we know that a radiation is a beta particle, an alpha particle, or a gamma ray? Okay, well, we use our Geiger counter to measure the click, and we know that obviously it's ionizing radiation. But if I create something called a cloud chamber, okay, this is a cloud chamber. So I make a very cold chamber of alcohol gas. Okay, you might see this in a museum. If I take a radioactive source and I put it by a cold chamber of alcohol gas, the alcohol gas forms like a cloud in the mixture. I'll show a video in class of this, okay? And when ionizing radiation goes through that cloud, it looks like a bullet. Okay, it flies, the ionizing radiation will fly through, and it'll cut the cloud like a bullet, okay, in the cloud chamber. So we can see ionizing radiation. We can see these alpha particles because they look like a bullet in the gas, and they'll fly right through. So if I take a radioactive source and I put it beside a cloud chamber, I'll get all these bullets flying through the cloud. The more bullets per second, the more radioactive that is, okay? But if I want to see what kind of radiation it is, okay, remember beta particles are negatively charged, okay, alpha particles are positively charged. There's a couple things I can do, okay? I can stick a positively charged electrode on the top of that cloud chamber. I can stick a negatively charged electrode on the bottom of that chamber. So if this was a beta particle, the bullet, instead of going straight through, is going to curve upwards. okay, then I would know that that type of radiation is negatively charged, okay? If it's positively charged, like an alpha particle, okay, it's going to go downwards. And it's going to be more steep because the alpha particle has 2 positive charges. If it's a gamma, what's going to happen? Well, if it's a gamma particle, a gamma photon, it's just going to go straight through, okay? And it doesn't get deflected by the positive or negative electrodes, okay? In contrast, we can use our knowledge of magnetism. So instead of electrodes, I can put a magnet up to this. So I have a north pole magnet, I have a south pole magnet cutting perpendicularly. The magnetic field is going through in that direction. We can use our knowledge of the motion of charges through a magnetic field. Okay, do you remember that the magnetic force is equal to BQV? Okay, and then the left-hand rule. Okay, so if I have a beta particle flying through this cloud chamber, which direction would it go? So if I use my left-hand rule, and I remember that it's a negatively charged particle, it's going to go opposite to what my left-hand rule is saying. Okay, so what's going to look like is that if I use my left-hand rule, it's telling me that that beta particle is going to go downwards. It's going to spiral downwards in a magnetic field that looks like that. Okay, the alpha particle, on the other hand, okay, is going to spiral upwards, okay, in that magnetic field. And of course, a gamma photon is going to go straight through because it doesn't have any charge. Okay, these are things that you could expect to see with radiation on an exam. They can give you a cloud chamber and ask you to tell them what type of radiation is coming off of that source. Okay, so you don't have these things. What type of radiation is coming off of that nuclear decay? And then you'd have to say, okay, well, if I put electrodes or magnets, I could see which direction that radioactive particle is going, and I could tell you what it is. And then the next thing we're going to do is, after I count the number of decays, I can understand the law of radioactive decay. Okay, so radioactive decay, when I look at an atom like this one, I can't tell you when it's going to undergo a decay. I can only tell you a probability of it undergoing a decay. So what's really important, if they ask you to define the radioactive decay, you need to say that it's random and spontaneous, okay? And that you can't actually say which atom is going to explode in a nuclear substance, a radioactive substance. You can only predict which atom will undergo radioactive decay in a specific period of time. Or you can't predict, sorry. You can predict the probability, okay? And so radioactive decay, the other interesting thing is I can't affect it by environment. So if I change the heat or I squish the substance or I really play around with it, it's not going to affect the rate of radioactive decay. Something happens internally. And we're going to learn in the next section about binding energy. It relates to how strong that nucleus holds itself together. And there's a couple forces inside of it, called the weak nuclear force or the strong nuclear interactions, which I want you to read about in your text, which help us understand why radioactive decay happens. So if you're asked to define this, the radioactive decay law, this is what you need to be able to write. The rate of radioactive decay is proportional only to the number of radioactive nuclei isotopes in the sample that have not yet decayed. Okay? In other words, the rate is proportional to the number of radioactive atoms in a substance. Okay? So if I have a substance that has 100% radioactive atoms, okay, I kind of drew this box too big, but if this is 100% radioactive atoms, okay, the rate is going to be very, very high. Okay, and then as those atoms decay, the rate is going to go down over time. Okay, so here's an example of what this would look like. Here I have a sample of cobalt-60, which undergoes a beta decay. Okay, remember that reaction. The nucleon number doesn't change. But if it undergoes a beta decay, a neutron becomes a proton. So that's why the element changed, okay, from cobalt to nickel. All right, so neutron became a proton and spit out an electron and an antineutrino, okay? So if I had a substance that was maxed out cobalt-60, I have 10 grams of radioactive cobalt-60 atoms, okay, that would be 100% of cobalt-60, all right? And then you'll see the rate depends on the slope, okay? So the slope of that is rate, okay? So if I look here, that's the slope there is rate. Okay, and as those atoms start to decay, the number of those atoms decays, so the mass of radioactive cobalt atom starts to go down. So as this graph goes down, I can say that the slope here is going to be half of what the slope is over there. Okay, so the slope over here is half, the rate is half, and the rate is half because now I have half the amount of radioactive atoms. And then the slope here is half of what the slope is there because I have half the number of radioactive atoms. And so on and so on. So the slope of the graph at these points tell me the rate of radioactive decay. Okay? And the rate of radioactive decay is becquerels, the radioactivity, okay, that I talked about, that unit, decays per second. So my Geiger counter would be screaming, and then it becomes half as loud, half as loud, half as loud, half as loud at these points. Okay, so at these points where the rate of decay is halved, we call that a half-life. Okay, so for cobalt-60, all right, after 5.27 years, that slope is going to become like this. That's the half-life. After another 5.27 years, the slope is going to become half. After another 5.27 years, the slope is going to be half, and so on and so on. All right, so that brings us to the idea of half-life. Half-life is the interval of time after which the decay activity of a radioactive sample is reduced by a factor of 2. So here I have that, I just have this graphic of what I was just talking about. At this point here, 100% of the atoms in my sample are radioactive isotopes. Okay, the half-life would be when half of those atoms underwent decay. And notice it's kind of random. It's not like the bottom half undergoes. Okay, so half of these atoms, 50%, have undergone the decay to the gray guys. Okay, and then if I looked at the slope, I see that the rates are half. Okay, so 50% of the atoms, and then another 50% of the atoms have decayed, and then another 50% of the atoms have decayed. So each one of these time points is a half-life. Okay, the time it takes for half of the number of atoms to decay is my half-life. Okay, and then I can't see the atoms in a sample decaying. I can only use my Geiger counter to give me counts per second. So at the beginning here, I have 70,000 becquerel. Okay, what is that? 70,000 decays per second. So 70,000 atoms are decaying per second. All right, and then if I was going to track the half-life would occur when I would have 35,000 decays per second. Okay, because remember, the rate of decay depends on the number of atoms. So if I went to half the atoms, I'm going to go to half the rate of decay. So at this point over here, let's put a better color here. Okay, at 35, that's my first half-life. So if I read the axis, it's in hours. So the half-life, which is T1 half, is equal to 6 hours. Okay, for this sample, whatever this element is, the half-life is 6 hours, which means that in another 6 hours, at 12, I should expect half. Is that true? So 35, yeah, it looks about true. Half of 35 is, I think, 17.5. So that's around 17.5. And then at 18, I should be half of that, which is going to be 8 point something. All right? And you can see that that definitely follows these trends. Okay, so the half-life is 6 hours for this substance. Okay, so let's take a look at a sample question with half-life. Okay, the activity of a sample is initially 80 decays per minute. The activity becomes 5 decays per minute after 4 hours. Calculate the half-life. Okay, so something I did with the group that was with me on Wednesday is I showed you how to do this conceptually rather than using formulas. So half-life means that the rate of decay goes down by half. So starting at 80, in one half-life, the decays will go down by half, as I showed you in this graph above. Okay, in the next half-life, it goes down by half again. In the next half-life, it goes down by half again. And the next half-life, it goes down by half again. Okay, so if I tracked the half-lives and all of a sudden I get to my 5 decays per second, I can count the number of half-lives that occurred. 1, 2, 3, 4. So in 4 hours, I had 4 half-lives. So to calculate the half-life, I take 4 hours divided by 4 half-lives. That means I have 1 hour per half-life. So that's how they can give you a word problem where you have to then work out what the half-life of that radioactive substance is. Okay, and remember that the rate of decay over here is going to be a lot less. The radioactivity of the sample here is going to be a lot less than the radioactivity of the sample here because there's less radioactive atoms. Okay, so I'd rather be around the substance here after 4 hours than in 1 hour. It would be safer for me to do so at this point. Okay, so that's essentially the SL version of half-life. The HL version, we're going to come back because they don't like to give you these round numbers. They'll give you a number where it's somewhere in the middle. And you actually have to use the exponential form because the decay is an exponential. It goes down by an exponential factor of 1/2, right? So you have to use an exponential formula to be able to then calculate. And that exponential formula looks like this, which I showed the group that was here on Wednesday. Okay, the number of radioactive atoms remaining is equal to my original number of radioactive atoms times that not divided by, but to the exponent of that and that, okay? And lambda is my decay constant. T is the time frame that we're looking at, okay? So we're going to come back when we do HL nuclear physics, and you're going to be able to look at decay reactions using this exponential decay formula, okay? And Malte and a few other students did an excellent job rearranging this equation to come up with a linearized formula for this, okay? So come to class on Wednesdays.